Greetings, class. This is an intro to VFDs. My name is Al Kesnoltz. I'm an instructor here at the UA of New Jersey. VFDs come in many different sizes and brands, but the fundamentals are usually the same. The terminology may be a little bit different between the brands, but the way they operate, okay, and the parameters should fundamentally all be the same. Same thing with the safety protocols with it. If you're viewing this as a PDF, then this click will be active and you could click on this orange font here and read a little bit more about fundamentals on VFDs, generically speaking. What brand of VFD should I use or you should use in the field? Well, that's all up to you and your company that you work for. Some companies represent and warranty certain VFDs, okay? Some have different buying power with multipliers that make it more attractive for them to use one brand over the other. Out of the 4 VFD drives depicted here, I'm actually certified in all 4 of these manufacturers. I will say out of all 4 of these, the Honeywell is the easiest to use, as the Yoshaka, if I'm saying it right, is probably my least favorite, but it's the most flexible drive and the quality on that is superb because it comes out of Japan. It does some really cool things such as it could actually heat the windings of your motor if your motor is in a wet environment without actually turning the motor or letting the motor spin. Pretty neat. ABB, Schneider Electric, as you know, those are very stable brands in the industry as well, especially when you get into larger machine rooms and air handler rooms. So we usually think of one VFD per motor, but things are changing now. You could get what's known as a fan bank that's depicted here on the left, where instead of having one big or 2 big indoor blower motors, now you have a wall, or it's called a fan wall, and you have multiple smaller motors in the airstream. So actually one VFD can control a few different motors, believe it or not, and they also do that in refrigeration. They put a series of VFDs on a few motors, and just when you're doing that, make sure the horsepower of each motor is added up for a total horsepower, and that drive would have to be able to operate that total horsepower. So basically it's not one VFD per motorized device anymore. There are some loopholes to this, and it's pretty neat how the industry is changing. But you can control multiple motors with one VFD drive if it's sized correctly. Seek out factory training. All right, it's going to make you a top tech. All right, the 4 VFDs that were in the previous slide, I was fortunate enough to get factory training on all 4 brands, and then also carry a factory certification. What does it mean when you're factory certified? Well, it means that you get to do a lot of startup work, which is nice, clean work. 2, makes you more employable compared to other technicians out there. And 3, it allows your employer to not only warranty what they put in, but get an extended warranty. For example, Honeywell would give a 3-year warranty based on if it was started up by a factory trained technician. So when I worked for previous companies, it was in their best interest to have their technicians certified on a piece of equipment, so therefore they could get the 3 years warranty out of that motor, no questions asked, or out of that VFD, I should say, no questions asked. But it's up to you to ask your employer and to seek out factory training. This presentation, as a side note, is designed only to be a general overview. It's not to substitute factory training. This is a very generic introduction to VFDs. And if you remember this movie clip here, it is of men who stare at goats. So if you want to be a selected few, you're going to have to seek out that factory training and be unique and offer something different within the trade. Remember, whenever we're working on VFDs, right, we're going to also wear our PPE, safety glasses, typically it's leather gloves, actually, believe it or not, and arc flash protection. Each company has their own rules and regulations in arc flash. Some companies give arc flash clothing in the sense of shirt and pants, whereas other companies will give overalls with a arc flash mask here, as well as double lined gloves. The first is a latex or a plastic lined glove, and the other one is a leather glove on the exterior. This is a safety bag. We also want to use proper true RMS meters with a category rating that is for the equipment voltage we are servicing. So we want to make sure it's true RMS, and we want to make sure that it's either going to be category 3 or category 4, depending on the type of equipment we're serving. So when I worked at UTC Carrier, we used all category 4, but we also worked on bigger starters and bigger motors. All right, for more information from Fluke, click on this orange link here if you have access to this PowerPoint presentation in a PDF format. When servicing a VFD, it's always good to refer to the manual. There are some cautions that we have to take into consideration. And I'm just going to read this verbatim. For some time, all right, the power is switched off. High voltage remains in the smoothing capacitor. We also call that the DC bus. When accessing inside the variable frequency drive for inspection, wait until the charge lamp is turned off, and we make sure the voltage across the main circuit terminals P and N is not more than 30 volts DC. Now, that's something to remember. That's DC. Remember, this is the DC bus. Some VFD drives have a little light in there that when the power goes out, you actually will see that light dim and then fully go out. And what that's doing is it's telling you the status of the DC bus. Some VFD drives do not have that. And that's where we want to use our meter in DC to make sure that there's no voltage present, not only on the AC side, but on the DC side as well. And follow company policy. So when I was working on bigger VFDs, ones that were the starter panels were as big as I was when you opened up the door, we used to have to wait 15-20 minutes for the DC power bus to to dilute itself and work its way out of the system. Whereas the smaller drives nowadays could be up to 30 seconds and they're fully dissipated. VFD drives could be inspected, and there are some signs here or some checklists to go here. If you were to servicing a VFD, they say in 10 years, change the cooling fan, all right, the main circuit smoothing capacitor, onboard smoothing capacitor relays. What I do want you to take out of this is that if you have your paperwork and you're working on a VFD drive, don't set your paperwork and your manuals on top of the drive. What happens is the drive has a little vent on there, exhaust fan, that uses ambient air to cool itself down internally. And a lot of times if you stick the manual on top of the drive, you block the airflow and then the drive is going to prematurely fail. So please make sure, safety-wise, that the DC bus is not holding a charge, that you allowed enough time for it to dissipate. You check it with your meter, both on AC and DC. Don't block the air vent on a drive with a piece of paper. And also know that just because the drive is not running doesn't mean that it's powered off. You got to remember you have two sources of power that's going to activate the drive. You have your 3-phase coming in, your L1, 2, and 3, but you also have a remote set of contacts, usually in a discrete run signal, that will wake up the drive and allow it to run. So you may go on a drive and it's physically not running, right? But it's powered on, it has power, but it didn't receive a run command from an external source. So note that you have your 3-phase turned off to the drive, as well as hopefully is not able to get a signal from a BMS or exterior source. The benefits of the VFD. Now there's more benefits than disadvantages. Did you know, okay, that if you reduce the power to a motor by 20%, you will reap the benefits of 50% in energy savings? That's correct. That's pretty awesome. And not only that, which this equates to 60 hertz being 100% output. If you reduce the maximum speed to 48 hertz, in return, you will reap 50% of the energy savings. So that's pretty neat. This is why we don't really have to run VFD motors at 60 hertz. Sometimes we don't run them at 100%. We run them much lower so we can reap the benefits. If we could get away with 50 hertz or even 48 hertz as a maximum speed, then we will then yield 50% of energy savings. That's pretty awesome. There's 6 primary benefits of a VFD. This is something that I took from a generic blog on the internet. The reason being is that there's more benefits than disadvantages. So what we do is we keep the starting current in control, which is very important. There is something that is known as peak load demand, when we can limit the amount of inrush current that a building um, utilizes. All right, they keep their utility bills down for that month actually. So we could keep the starting current in control, reduces the power line disturbances, demands lower power on startup. It helps in controlling operating speed and acceleration. All right, it limits it and adjusts the torque, which is pretty neat. We had a technician call the school saying, "Why does my motor keep chewing up the belts?" I go, "Well, is the motor starting and stopping? Like, is it on auto on the thermostat, or is it on continuous run?" He goes, "Well, it's on auto." Well, that means that every time your motor starts, it's starting at 100% because it's not on a VFD, and it's chewing up the belts because it's slipping and it's just starting and stopping more than it should. Well, we could limit those torques on startup. All right, we can protect the drive and the driven shivs of the system. We also save energy and cost. All right, as we said before, if you reduce the power by 20%, you will save 50% in energy costs. So 48 hertz as maximum speed will save 50% in energy costs. Disadvantages, there's not much there for disadvantages other than upfront costs. A customer may not want to invest in a VFD drive because it costs too much money on the initial purchase. It may lead to uh, resonance at certain speeds, okay, which is known as noise or harmonic distortion, and it could also lead to excessive vibration. Typically, that happens, okay, the resonance happens on motors that were really not designed initially to be on VFD drives. There are motors that are sloppy and their service factors are not that clean. So by putting a VFD on a older non-VFD rated motor, this is bound to happen, and it is some of the side effects. So we call it noise or vibration, also known as harmonic or resonance. All right. It's said that the VFD has been known to shorten the life of the motor. That could be true, but also a false statement. There's some things that you could add to the system to lengthen the life of the motor. Typically, what happens is the motor has been running conventionally all this time. We put a VFD on there, then we might reduce the lifespan of it by converting it from a conventional to a VFD motor. But if you started off with a VFD rated motor from the beginning, there is no real shortening life on it. Actually, it is said to extend the life at that point. And it can reduce the service factor on the motor it's used on. So this is what we need to know about grounding rings, okay? This is something that you're going to see on your STAR exam when you're going to be in 5th year. It's an add-on that we could put on to variable frequency drive motors. VFDs are more susceptible of obtaining bearing failure, as the previous slide was saying. Right, it's generated by the sine waves. The voltage is balanced, which means that the amplitudes of the waveform on both the positive and negative sides are equal. So in pulse width modulation generated sine waves produced by VFDs, the voltages are not balanced. Right? That imbalance from pulse width modulation is how we rectify or make a motor spin at different hertz. The imbalance could cause a voltage potential in the motor structure, leading to the voltage passing between the rotor and the stator to ground through the motor bearings, causing damage. And some of the damage would be a bearing pitting, um, SEM image of that particular pitting, bearing flute damage, and EDM pitting. So the solution then is to add some products here, right? And VFDs.com does sell it, all right? And it's called a shaft grounding ring, or it's sometimes known as a shaft grounding strap, right? So this grounding ring is placed near the end of the shaft, as depicted here in Figure 2, and carbon fiber brushes attached to the ring contact of the shaft. The brushes now become the easiest path of ground, all right? Remember, electricity follows the path of least resistance. So it's going to, instead of going through the bearings, it's going to go through the shaft ring. and the shaft ring then is then grounded to earth ground. Okay, so no current passes through the bearings, which eliminates bearing failure caused by the unbalance of the pulse modulation wave. You're going to need to know that possibly for your STAR exam. Now, I'm just going to go over some rules of thumb, and these are just rules of thumb, okay? And this is how to configure a VFD, just so you can get started. But each job may be specified or spec'd differently, so take that under consideration. All right, number one, okay, we want to understand the motor parameters. We can't do anything unless we know what the motor is rated for. We tune and program the drive to the motor parameters, right, such as RPMs, horsepower, max current, service factor. All these are things that we have to take in consideration so we can actively match the drive to the motor, especially if you do a motor replacement and you're reusing the same drive. Well, that may not be an exact motor replacement. You may have substituted an A.O. Smith with maybe an Emerson or US Gold motor. And in doing so, all right, you're going to have to change the VFD to meet the motor parameters. Then once we have the motor parameters down, we have to understand the VFD parameters. What can this particular VFD drive brand do? Okay, and how is it done? Because ultimately we have to go through the nomenclature of that one particular drive brand to make it acceptable where we can input that information from that motor information nameplate. Then once we know the motor, okay, and the drive parameters, we have to know how is it being controlled. Is it going to be initiated from a BMS, start stop command and speed reference, or is it going to be based on the equipment? For example, you might see VFD drives on a carrier unit, carrier's MMB board, or the board that's located near the economizer section control the operation of the VFD drive. It is done internally within the unit. Same thing with an AON. Okay, they will control the VFD drive with its own internal software and control logic. Whereas if we're adding this to a site, we may be controlling it through a BMS, through an external means of operation. So what we have in the shop for you, which is pretty neat, is we have a little VFD trainer. We're using it, it's from Westinghouse, it's an L510. What makes this a little special is that it's a 115 volt single phase input. And take notes on this because this might be one of your questions here. So it goes in at 115, and what is our output? We can control a 3-phase up to 1/4 horse to 1 horsepower. It's pretty neat because the L stands for lathe. This is how people could put a VFD on a lathe wood spinning machine, where they can then take a 115 motor, remove it, put a 2.8 volt 3-phase in there, anywhere from 1/4 horse to 1 horsepower, and it uses a normal 115 outlet. Pretty neat, but the pulse modulation on the 3-phase side remains the same. Same type of theory, same technology. Terminology might be different between Westinghouse and the other brands, but ultimately we're going to set it up the same way. This is what you're going to look for in the shop. This is the VFD board. And as you can see here, it's actually on a 115 outlet plug, and it controls a 3-phase motor over here that's rated for 208, 230. And we have a little rib relay here. The rib relay is called the pilot relay that will initiate the start-stop command to the drive. We have a thermostat here, basically a normal stat. G will make the stat. G will feed to the rib relay, and then from the rib relay, we pilot the operation on this with a discrete input point, start, stop, run, forward, and then we configure the drive in here for the nameplate information. Pretty simple, but yet effective. So let's understand what we're looking for in the motor parameters. This was step one. If we look at the motor nameplate here, all right, we see that it's a 3-phase motor located here. We also see that it's a 1/4 horsepower, 0.25 HP. Some VFD drives like the Westinghouse, you have to set it up for KW, which is not a big deal because the KW is there if we need it. It's 0.18 KW, but most drives are horsepower. All right, we also need to know the RPMs, 1765, which is also important because the drive needs to know how fast it needs to rotate the shaft in the motor. We have to choose our voltage. This is the output voltage, and this particular VFD drive will produce 230 volts, so it's a 230 volt motor. And we have something here called amperages and service factor amps. This is nice because this particular motor gives you your service factor amps. Your service factor amps is going to be the maximum current that that motor is rated for. Service factor has to do with how clean and efficient the motor runs. Typically, you'll see a service factor of 1.15. This particular motor has a service factor of 1.35, so it's a little bit noisier and dirtier. But keep in mind that this is only a $100 motor. That's three-phase, so keep that in consideration. We got it from Johnstone. If you did not have the service factor amp, and a lot of motors do not have the service factor amp, you will take the normal running load amp of 1.07 and you would times that by your service factor, which is 1.35. You're left with a higher amperage than your running load amp. You have what's known as a service factor amp. Let's just recap this again. Your normal amps would be 1.07. Now when you times it by your service factor amps, you're left at 1.44. So your maximum current for this motor, when you program it in the drive, has to be set up for this amperage here, including your service factor. So the normal maximum will be 1.44. Anytime it would go over that, then the drive would either try to protect it on a safety, or if it continues to rise above that, it'll trip on a fault and try to protect itself. All right, and this will go into how to get your service factor amps. It's basically, we're looking for the max current this motor can run at so we can program it into the drive. A little bit, we'll just do it one more time because a lot of people have a little trouble with it. Okay, this is not lock rotor, but let's call this running load amps or full load amps. Okay, under normal operating conditions, we would take the amperage on the nameplate, we'll times it by the service factor. Remember, most motors are 1.15. This is 1.35. And that's going to give us our max current amps, also known as service factor amps. And like I said, the good thing is this motor here has the service factor amps already built into the nameplate. If it did not have that, then you're going to have to take your amperage here and times it by your service factor right there. So let's understand the VFD parameters, okay? You have either an installation manual or a startup manual. Each one has its own set of information in there. Typically, the instruction manual will give you what you need to do a quicker type of startup, whereas the other manual will go into more depth in the menu system. But based on this particular diagram, let's take a look at it. This is L1, L2. The L3 is not being used. We only have 2 wires going into our drive, which would be a 115 drive, but notice how that they use the same type of diagram with different notations on it. There is a set number of inputs here, okay, predefined set number of inputs called digital input. All right, and we have our forward command. This is where we would want to do a run forward, run reverse, which we're not going to run it in reverse. Then you have preset 1 and 2, and then a reset over here. Now you could use a reset in case you had to do a remote reset of the VFD where you don't have to physically visit it. There's an external analog inputs. Analog inputs are going to be your 0 to 10, 4 to 20. And this is how we're going to control the speed if it's set up correctly in the parameters. We have an analog output that we could use here for feedback or for fan tracking where we want to wire in multiple VFD drives in piggyback orientation. And we also have a multifunction output relay, which is really neat because we could use this as an alarm relay output, so we know if there's a failure on the drive. And we have an RS-45 communication port. Some drives could do Modbus, they could do BACnet, they could do LAN. So you could actually have a BMS network that you could talk and network the drives independently. But we also want to understand the terminal layout. So on this terminal layout, right, we could also look at this particular diagram here. These are our inputs. that are binary, discrete. These are inputs that are analog. So if we come over here, notice how we have S1, S2, S3, S4, S5. Okay, these are switch 1, switch 2, 3, 4, and 5. And this is the common to the switches. So to do a run forward command, we would go from common to S1 for a run forward command. A run reverse would be common in S2. If we had it networked and communicating, we would use RA and RB. And these over here, this is a 10 volts. This is this generates its own voltage DC, where then you could use it as a current sync loop, something that we could talk about in the future. But because it generates its own voltage output, you could then run that to a transducer in the case of a 4 to 20 transducer, and it could come out, it could then return as an analog input under 4 to 20. But it's pretty neat that it has its own voltage supply, so we don't have to use a DC generator for this particular application. AVI stands for analog voltage input. Right, this is where we would do a voltage 0 to 10 speed reference signal going into the drive. You have an analog current input, ACI, where that would be for a 4 to 20 input for a speed control reference. You have an analog output, so you could actually use that for status, or if you want to do it for fan tracking, you could go in this drive as an input. You could take your output and feed it to a BMS system or another motor that could actually run off this VFD drive, and this would be the ground to that terminal block. So this ground is shared between 10 AVI, ACI, AO, and ground. And then this terminal here, 5, 4, 3, 2, 1, and common are shared together on that terminal block. So how do we start the VFD? We want to get it to work, right? We understand that we need to have the motor's information, the drive information, and now we have a bunch of terminals. What theory do we need to do to get this to operate? Well, the most common way to start the drive is to use a discrete input. You'll see me either use DI or BI. All depends on who's writing the instruction manual. SS stands for start stop. That's all that means. So DI with the emphasis on the I means input. Discrete or binary means the same thing. We need to have a clean, dry contact closure. We could obtain that with a rib relay. We could obtain that with an isolated relay that is gold plated. It needs to be dry, meaning that it cannot be shared with any other relay. And for us to do this, we would wire S1 to common, and we would provide a dry contact here. So we could do it with a rib, we could do it with a cube. We cannot share that switching with anything else, okay? And it cannot be what's known as a wet contact. Here's a wet contact. Ruben does a great job talking about this. You need to understand the theory of a wet contact for the STAR review. All right, a wet contact is something that shares multiple relays, okay, usually on the common side or the neutral side of the switching. And it cannot be a triac either, okay? The reason being is this is a DC voltage signal generated by the VFD drive. It can't be shared with any other switches along here, okay? It could not go on a triac. A triac is only for AC switching, AC. Look at this, triac. Triacs are only used for AC, alternating current, all right? And it cannot be used on a wet switch. Usually wet switches are triacs. All right, but it cannot be used in this situation either. You need an isolated relay for a particular switch that it needs to make on its own independently. Okay, so we call that a dry contact closure. We don't share it with anything else. That's a symbol of a triac right down there. So, and this is what a wet contact looks like. Control and automation. How do we control a VFD? Absolutely, with control and automation, right? So we know how to start stop, right? We start stopped it on the run forward command, but we also need an analog input to control the fan speed. Yes, you could do it in hand mode. You start stop, run it in hand mode, and then you could dial up the potentiometer. That's one way to do it. But we would also want to have a little bit more control from an external source. So here's a 0 to 10 volts DC. It is polarity sensitive, so this would be the positive. okay? And this would be the negative. And when we go to the bench and do it on the shop, we're actually going to give you a 9-volt battery. Now you may not get the full 100% output, but at least you'll get 90% out of a 9-volt signal versus 10 volts. You could also use a signal generator. If we were to use 4 to 20, all right, we would then land the positive of the 4 to 20 here and the negative side of the 4 to 20 here. There are advantages and disadvantages, okay, to both signals. I would say at this point of your career, if you can wire it up with DC, it's better. All right, for all of us, because you could take a DC meter and you could read voltage across the line without drowning out the signal. If you're using 4 to 20, you have to measure 4 to 20 in series because it is a current signal. It's milliamps, and you need a special meter to be set on milliamps to read it. A lot of times the fuses get blown and you don't realize it, and you're working with a meter with a blown fuse on the milliamp side, and you're really going down the wrong path. You're doing more damage than good. So if you could use 0 to 10 volts DC, it's a lot easier to troubleshoot, and it's a lot easier and more convenient to work with. All right, but there is some advantages why we use 4 to 20. It's because it could go longer runs and it has less EMF interference. But if you're working in the confines of like 50 feet or less, you're fine. Now, we're going to now need to know, is the drive running? Okay, we need to have a status. Is the drive running? Okay, so we could use the internal relays on the drive, or we could put external devices in. All right, so I highly recommend using external devices. The reason being is it frees up this multifunction relay output, because we could use this as an alarm or an alert output. If we use it as a fan status or a status point, we take it out of use, whereas it's more important to use it somewhere else. So some of the external devices that will add to a system is maybe a little CT called the Hawkeye. We're going to put that around the motor windings, or the leaving wires going to the motor that will sense amperage, okay? And it will let us know if the motor is running. Something even more effective would be actually a velocity transmitter, all right, that will know that there's actually static in the ductwork. Because what could happen is you could start the VFD. If it's a fan powered VFD, it could get through the belt, or the belt could be damaged. We still measure status that it's running through the output of the drive, but yet there's no rise in static air pressure. And what could happen is we could actually start the cooling process, and it's called equipment staging, without truly knowing whether or not the drive is truly running. So the way to know the drive is truly running is that it's truly moving airflow. And one way to truly know it's moving airflow is to put a velocity sensor in. So then we know we got up to our target of 1 inch of static. Then let's start staging up our compressors and opening up our liquid line solenoid valves and starting the direct expansion cooling process. If we didn't know that and we based it on a CT or a relay coming from the drive, we can initiate a cooling sequence even though we're not moving air, if you know what I mean. So external, and when all possible, a transmitter that would measure air velocity is the right way to go. Like I said, we want to also include some sort of failure and alarm system. A failure and alarm would be an output on the drive. It's going to be a discrete or binary output going into a BMS system or an alarm panel. And we could continue to use, and I highly recommend using the relay output on the drive. We will know that the drive failed, all right, internally. And if we also installed, okay, for status inputs, a CT status, also known as a Hawkeye around the wire, or a velocity sensor, we could also generate a second alarm when we don't have a proof of movement of the motor, okay? Because you might get an alarm on a motor on the VFD drive, but it still might run. It may be like a soft alert versus a hard failure alarm. So by doing it this way, you get a relay output from the drive, and you also get a status that will not coincide with the run command, and then therefore you'll have a better alarm system built into your BMS. We also have an analog output on a drive. This particular drive is allocated for 0 to 10 volts DC. Other drives are configurable. It could be voltage or it could be milliamps. All depends on the model you're going to be using. If you ever worked on the large McQuay units, and this, when the supply fan activates and it runs, it sends a analog output to the return fan. And what it will do is it'll do fan tracking. So as the output or as the speed increases on the main supply fan, this output here from the main drive will go into the input of your second VFD drive, and you could set it to be 1-to-1, or you could set one fan motor to run a little bit higher than the other one, especially with return fans. Also, you could bring this back to the BMS system and have a percentage returning back. So if you told the drive that you wanted 40 hertz, okay, hopefully when you tune it, you get a feedback that it is running at 40 hertz back. Or if you have to go into one drive 4 to 20 as an input, okay, 4 to 20, one of the disadvantages, you can't share that signal, okay? It's only one signal for one drive, whereas voltage, you could kind of splice into it. You could have 3 drives receiving the same voltage signal. So you take a 4 to 20, go to a drive with 4 to 20, come out 0 to 10, and then feed that to another drive if you had to branch off. Okay, it could also act as like a like an extension cord, right? Where we're splicing the outlet and we're going out to more drives. So that's an option. That's an output. Sometimes you could use that. Normally we use it for feedback going into a BMS system, so we know the percentage of where it's running. There are some rules of thumb now when we start using or setting up the drive, okay? And these are just rules of thumb, and it's going to help protect the equipment. We usually put 60 seconds on the acceleration, 60 seconds on a deceleration time. So when you give it a speed reference signal and it has to adjust, it has 60 seconds to get to that adjustment. And it's 60 seconds to go back if you overshoot. This eliminates hunting back and forth. And this is field adjustable because sometimes you do have to tune it. 60 seconds may be too short in some cases, and it could be too long in other cases. But a good starting point is 60 seconds of time delay on acceleration and deceleration, and that's configured in your drive. We also say that a motor should never go below 20 hertz, especially if it's an air-cooled motor. All right, we need to keep the paddle wheel on the end of the stator spinning, so we have cooling and ventilation going on, and we could cool the motor windings. There are some instances where you might have a specialized motor and it's factory sealed. In that case, do what's recommended on that particular type of equipment. But if it's air cooled and you don't know where to set it, 20 hertz is the absolute minimum on an air cooled motor. You could always go up from there, and not to exceed 60 hertz on a normal run cycle. So 60 hertz would be as if we were telling the motor to run at 100%. You also have to go into the menu system on the particular drive, and you want to open up the drive a little bit, okay? On this particular one, all right, they call it different terms, but what would happen is the drive comes from the factory with every bell and whistle activated to protect the drive. Remember, the drive manufacturer wants to protect their product. What's going to happen is if you don't go in there and then you open it up where you could have what's known as momentary power loss restart, the minute you leave that job site and you get a power failure, that drive is going to restart and be locked off, meaning that an operator would have to go there and start the drive. That's great if that drive is spec'd to be that way, but it's a callback if you leave and have to come back just to restart the drive again, because you're going to eventually have a power failure. So you may have, there's a setting in there that you have to go in there and you have to enable a momentary power loss restart, okay? This way it goes back to normal after a power outage. Also, there is an auto restart delay. We don't want it to start up automatically, okay? When it fails or there's an alert, you want to give it some time delay to have maybe the voltage is imbalanced and needs to rebalance again. We give it anywhere from 3 to 10 seconds. We don't want to restart this thing right away because it may be controlling a big motor. So we have to lengthen the auto restart time delay. The number of attempts, we don't want to give it just one attempt to try to auto restart. We want to maximize it to whatever the maximum could be. On the L510, is 10 restarts. Let it try to restart over and over again. There's a 3 to 10 second delay. All right, if there's truly a problem, it's going to try to restart 10 times and then physically lock out permanently, and then it'll give you a failure alarm. But let it try to restart. There might be a temporary brownout. It might be a temporary voltage imbalance. It could be a temporary line problem. We don't want to go back for nuisance service calls if it's not necessary. And we also want to maybe allow it to do a direct run after power up. Do you want it to then restart its sequence of operations if the contact closures are made for a run forward command? Absolutely. Let the BMS system determine when it can run and when it can't run. When all else fails, call tech support and take notes. This is the key. You're going to get more information, OJ, on the job training, OJT, if you have the number of the hotline, if you could schedule your VFD changes for a normal working hours. The worst thing that could happen is you go there on a Saturday or after hours when the building is closed and you go to do a drive. And you open up the book and you're like, whoa, I don't know what the terminology means between this manufacturer versus this manufacturer. I don't know where to start. If you have all your parameters of your motor written down and everything that you want to do and want the drive to do, if you call tech support, they'll walk you right through it. These are notes I took, all right? I called tech support Westinghouse. I said, look, I got to do a trainer out in the shop. How should I set this up? 20 minutes later, they walked me through it. I took notes. Now, basically, we're experts on this now, right? 20 minutes of training over the phone. I got these notes. I scanned them, made digital copies. Those are mine forever now. So take notes, archive your notes, all right? Get some training over the phone and work with tech support. They're there to help you. So let's summarize real quickly what the inputs of a drive should be and what the VFD configuration should be. Starting with the inputs, okay, we have a start-stop signal. We have to tell it to activate or deactivate, and it has to be a binary contact closure, and it has to be a dry contact closure. We also have to tell it how fast that particular drive needs to be or to run, and that's going to be our speed input signal. Those are called inputs. In return, the drive should also leave with information to the equipment or to a BMS system. We want to monitor and make sure we have alarms coming out of the drive. And we also want to know that the drive is actually running. Remember what I said earlier, we could use the drive as a status point, but it's better if we use the air source or the water source as a status point, because then we'll know that we're physically moving something versus mechanically giving something power. All right, now there's options here. We could add communications for networking, and we could also use the feedback known as an analog output to also have better control and monitoring of the VFD drive. When we talk about configuring the drive, on the left-hand side were physical inputs and outputs connections. When we configure the drive is then programmed in the menu system. We said earlier that the motor should have a minimum and maximum hertz, right? We should never go below 20 hertz, especially on air-cooled motors. The motor max current is the maximum amount of current allowed to program into the drive, so the drive doesn't let the motor go over that max current, or if it goes over that max current, it can help throttle it down or shut itself off. And the max current is going to be your run load amps times your service factor. Your motor voltage, you're going to need that. Your RPMs of how fast the motor is going to be spinning. What hertz you want to set it for. Typically it's 60 hertz. We have our acceleration, deceleration times. All right, rule of thumb is 60 seconds. We want to auto start the drive. We have to set it up for auto start and maximize the amount of attempts that it can auto start. Just don't let it make it one attempt. Auto start delay should be 3 to 10 seconds. And we want to enable direct run after power up. What's going to happen is if you leave the job site and you do not power up that, if you do not set that, you're going to get a callback, all right, which means that every time you had a power failure, you're going to have to manually start it. We want to enable that for a direct run after power up. And one other thing you want to consider, do you want it to break or you want it to coast. This is the stopping capability of the fan. There's pros and cons, so just usually we say coast to stop so we don't damage the equipment. But if you need a quick emergency brake, such as a smoke alarm, you could have that option as well. All right, based on this PowerPoint presentation, please proceed to doing the questions in the Blackboard assignment. Thank you so much.